Good morning, class. In the last video, we have studied about the principles of spoilage with respect to the perishable, non-perishable, and semi-perishable foods, how the number of microorganisms affects the spoilage quality or the type, how it's kinds of different kinds of microorganisms, their environmental conditions, their physical state, structure of the food, their associative growth, their behavior in the environment of food. All these we have studied. I hope you have revised once before watching this video. Continuing further, we will deal with how the nitrogenous organic compounds changes with respect to the food and microorganisms, and then bring in a change which leads to the spoilage of the food. As you all know, most of the nitrogen in food is in the form of proteins, right? So these proteins must be hydrolyzed by enzymes of the microorganisms or of the food, whichever is, because in food also there are some enzymes to polypeptides, and these polypeptides will be broken down to simpler peptides or amino acids before they can serve as a food, like nitrogenous source for most of the organisms. So generally we write proteins with the help of proteinases. Okay, uh, converts itself to peptides. This peptides imparts bitter taste to the food, right? And these polypeptides, with the help of peptidases, enzymes are peptidases, will be broken down to simpler peptides, and these simpler peptides to amino acids. Anaerobic, we have also heard of the process of putrefaction, right? The spelling is wrong there. So, anaerobic decomposition of proteins, peptides, or the amino acids, whichever has been reduced, may result in the production of a very obnoxious odor. And this process is called putrefaction. E is missing next to R, please add there, and these will produce hydrogen sulfide. That is why this smell, obnoxious smell, that H2S smell will be there. When microorganisms acts on these amino acids, they may deaminate them or decarboxylate them, or can do both, deaminating and decarboxylating. A very good example is when E. coli. Okay, well, let us see when amino acids are acted on. When when E. coli acts on glycine. For example, we will take glycine. We will take many things, alanine, glycine, serine, and C. When E. coli acts on glycine, they produce glyoxylic acid, acetic acid, and ammonia, right, from glycine. So when we see, when the same thing, when the glycine, the same amino acid is acted upon by Pseudomonas, the products are different. It is not like glyoxylic acid and acetic acid and ammonia. It is methylamine and carbon dioxide formed. So when the same glycine is acted upon by Clostridium, then the products are acetic acid, ammonia, and methane. So here it clearly states that it depends on the organisms acting upon these amino acids. Let us see the alanine. In case of alanine, what happens when E. coli acts on alanine? What is formed? Alpha keto acid, ammonia, and carbon dioxide is formed. When the same alanine is acted upon by Pseudomonas, acetic acid, ammonia, and carbon dioxide is formed. Same with Clostridium, the same alanine with Clostridium forms propionic acid, acetic acid, ammonia, and carbon dioxide. Right? So please observe that the amino acids remain the same, but the organisms acting upon these amino acids are different, leading to different byproducts. So these different byproducts will produce a different spoilage, different types of spoilage. I'm sorry about the arrows misplaced. It was something else in the laptop, and when I transfer it to mobile, it became something else. Then coming to serine, when serine E. coli is acted upon, when serine is acted upon by E. coli, what is formed? Pyruvic acid and ammonia is formed, right? And when Clostridium acts upon this serine, propionic acid, formic acid, and ammonia are formed. When sulfur in amino acids gives sulfides or mercaptans. So these are all the different things which will be different in metabolic byproducts. Coming to other nitrogenous compounds, what happens we will see. Generally, the other nitrogenous compounds includes amides, imides, and urea. Okay, from which ammonia is the principal product. Guanidine and creatine yields urea and ammonia. Amines, purines, and pyrimidines yields ammonia, carbon dioxide, and organic acids. These are all the other nitrogenous organic compounds. Let us see with what happens with non-nitrogenous organic compound. The main non-nitrogenous food for all our microbes mostly used to obtain energy but serves as a source of carbon includes carbohydrates. I had spoken about these things, the simpler one when we were discussing the intrinsic factors, right? So carbohydrates, organic acids, aldehydes, ketones, alcohols, glycosides, all these, even cyclic compounds and lipids, these are all the non-nitrogenous organic compounds which microorganisms depend on for different sources. Carbohydrates, if we take, these are preferred by microorganisms to other energy yielding foods. Complex di and tri and polysaccharides usually are hydrolyzed to simple sugars before utilization. But the most preferred one is the glucose because it need not be further modified to be assimilated. It can be assimilated as such. Glucose undergoes oxidation and forms carbon dioxide and water. This is aerobic changes. Aerobically, glucose is oxidized to carbon dioxide and water. But when a monosaccharide glucose anaerobically undergoes decomposition, what happens? In aerobic condition, it is a very simple process. Anaerobically, there are different types of fermentation which actually sets in. What are all those different types of fermentation should be known to us because these different types of fermentation sets in different types of spoilage and we should be educated about these things to design the different types of preservation in an anaerobic condition, right? So one by one, I will just give a glimpse of what happens in this different types of fermentation. Alcoholic fermentation, if at all there is an alcoholic fermentation of a glucose, right? The products formed are ethanol and carbon dioxide. Lactic acid fermentation, if it undergoes lactic acid fermentation, lactic acid, ethanol, and carbon dioxide are formed. I have used all short forms to fit in the PPT slides. So lactic acid fermentation leads to lactic acid, ethanol, and carbon dioxide. There will be sometimes mixed lactic acid fermentation wherein lactic acid, acetic acid, ethanol, glycerol, and carbon dioxide are involved, and the byproducts are this. Coming to the coliform fermentation. In coliform fermentation, the byproducts will be lactic acid, formic acid, ethanol, carbon dioxide, hydrogen, acetone, and butadiene. These are all the products formed. So you imagine the type of spoilage which sets in because of the coliform fermentation, right? Coming to propionic fermentation, this gives propionic acid, acetic acid, succinic acid, and carbon dioxide as byproducts. Butyric butyl isopropyl fermentation. This is also a type of fermentation which sets in. Butyric butyl isopropyl fermentation. This gives, all these are mentioned here. See, butyric acid, acetic acid, carbon dioxide, hydrogen, acetone, butylene glycol, butanol to propanol. These are all the byproducts of butyric butyl isopropyl fermentation. Okay, then still more complicated, the spoilage will be still more complicated. Coming to the organic acids, many of the organic acids, usually occur, that is in foods, occur as salts, right? And these salts are oxidized by organisms to carbonates, causing the food media to become more alkaline. Yes or no? Wherein organic acids are aerobically oxidized to carbon dioxide and water. It can be saturated fatty acids or ketonic derivatives, which will be degraded with the coenzyme called acetic coenzymes, giving acetic acid and carbon dioxide as the byproduct. When we look into other compounds other than these organic acids and other things, alcohols are oxidized to corresponding organic acids. For example, I have mentioned here ethanol gets oxidized to acetic acid. Glycerol get oxidized to glucose products. Coming to acetaldehyde, this is oxidized to acetic acid and reduced to ethanol. If you take lipids or fats are always hydrolyzed by microbial lipase to glycerol in the previous slides I have told, and fatty acids, which is then disseminated. These microorganisms are involved in the oxidation of fats, but auto-oxidation is more common. Right? What happens? Example I'm giving. Any phospholipids. For example, choline. You can take choline as a phospholipid. This actually gets degraded into phosphate, glycerol, fatty acid, and nitrogen bases. So, a different types of spoilage sets in. Coming to pectin substances, what happens if it deals with the microorganisms attack pectin substances? Protopectin is the water-insoluble parent pectin substance in plants. This is first converted to pectin. This pectin is a water-soluble polymer of galacturonic acid containing methyl ester linkages. Okay, this methyl ester linkages will be broken down by pectin esterase, causes hydrolysis of methyl ester linkage of pectin to yield pectic acid and methanol. Okay. So this polygalacturonases destroys, these are all the enzymes I'm talking, pectin esterases, polygalacturonases, all this destroys the linkage between the galacturonic acid units of pectin or pectic acid. This will yield smaller chains and ultimately free D-galacturonic acid, which may be degraded to simple sugars. So please, I repeat, protopectin is a water-insoluble parent pectin. This is actually converted to pectin, that is water-soluble. And this is a pectin is a polymer of galacturonic acid containing methyl ester linkages. This pectin esterases causes the hydrolysis of the methyl ester linkages of this pectin to yield pectic acid and methanol. After pectic acid and methanol, polygalacturonases destroys the linkages between galacturonic acid units of pectin, or it can be pectic acid also, to yield smaller chains further and ultimately free D-galacturonic acid, which may be degraded into simple sugars. This is what is the fate of pectic substances when microorganisms attack pectic substances in case of plant food, right? So these all different kinds of substances yielding to the degradation, whether oxidation or reduction or anything, other compounds, organic acids, nitrogenous, non-nitrogenous acids, all these things leads to various types of spoilage. And that is why all these factors will have different effect on the different types of spoilage. Further, when we start studying spoilage of cereals, spoilage of vegetables, spoilage of other food materials, we have to keep all these general principles in mind, that when it attacks a plant food, what happens? When it attacks an amino acid, what happens? When it attacks a nitrogenous substances other than non-nitrogenous substances other than amino acids, what happens? So if you keep this somewhere in the corner of your mind, it becomes easy for you to understand why organism is forming this and why this type of spoilage is set in certain types of food material, right? So this ends the general principles of food spoilage, and later we will see how individually all the types of food get spoiled. Until then, thank you.